Yes.
Okay, so I'll talk about improved Hamiltonians for quantum chemistry. This is something that I've worked on all the way since I was in graduate school. This was one of my first papers as a graduate student. Here are some references of some of the work that I'll be talking about. I'll start with just some sort of general issues about converging both in getting the correlations right and in the basis set size. And then talk about wavelets and our gausslet basis sets for use with DMRG, and potentially quantum computing, and then say a little bit about where we're trying to go. Okay, so this is starting off with some results from, we had our Simon's collaboration had a paper on the hydrogen chain doing benchmark results with lots of different methods. And we made a database, and I collected them just to sort of show the range of results that you get for H10 at R equals 2. And so what you see is, of course, we have the energy on the y-axis. The x-axis is just an index number for the method, which are all sorted by the energy value that was obtained. And the first group of black circles is the double zeta basis, which has 5 functions per atom, or 50 basis functions. The most accurate was the DMRG, which was done by Garnett's group. And that sort of set the benchmark, set the line. And you can sort of see how the different methods sort of converge to different sorts of accuracies to this method. But this is all at the double zeta level. And so I don't show triple zeta, but at quadruple zeta, the first thing you see is that there's a lot fewer methods. The methods as you make, so the quadruple zeta has about 300 basis functions. A number of the methods have dropped out, including the DMRG, just because the calculation is too big. And then you're still not there completely to where you want to be. If you go to 5 zeta, then there's only 2 methods left. And then you can try to extrapolate, and this is the estimate of the complete basis set limit. Okay, but so you see this sort of, this is for just one fixed system. We're trying to converge in both directions, and it's a challenge. And of course, then on top of this, you'd like to converge perhaps in the number of atoms, but that's separate. So the key thing is that this most accurate treatment for the low basis set completeness stops at triple zeta, and so that's unfortunate. And so we'd like to improve on that. So let me say a little bit about the quantum chemistry DMRG. Started with my work with Richard Martin back in 1999. It's been improved a lot since, with people quite a bit represented in this conference. But the key technical issue is that there are end of the fourth interaction terms. This is just the standard form of the Hamiltonian in a basis set. The end of the fourth terms directly affects the complexity of the DMRG calculation. There are tricks that you can do, and some sort of naive no-trick estimate might be scaling as the number of basis functions to the 5th power, but with tricks you can get it down so that the dominant term is n cubed, and m is the number of states you keep, which is generally bigger than n. So this is the dominant term. So back then we could do a system, just a water molecule, a stretched water molecule with a basis set of size 25. The progress in a couple of decades has been that that people can do, say, 100 to 200 active orbitals, which can be selected from a bigger Gaussian basis. And so you can do pretty interesting problems if you let much of the system be not correlated. But this is in contrast to Hubbard-like models, where the calculation time scales as n. And so 10 to the 3, 10 to the 4 would be fine if you had some reason to go that big for a chain in a Hubbard model. So so the point is that the Gaussians are highly optimized to reduce n. One doesn't pay so much attention in constructing Gaussian basis sets about the number of Hamiltonian terms, just accept this n to the fourth. And that's not a given, because if you just look at a simple grid, simple grids have n squared interactions, although you'll need a much larger n. So we've developed Gausslet bases to try to sort of reach an optimal point that's more favorable to DMRG in terms of sort of the number of terms, and also with the idea that this could apply to tensor network methods such as PEPs. But at the same time, they could offer advantages for quantum simulations. Okay, let me take a little detour into something with wavelets. So this is explaining a close connection between quantum circuits and wavelets. So suppose we were thinking along the lines of starting with the Hamiltonian with the favorable scaling, a grid, but we wanted to decimate the grid thinking in an RG sort of framework. But one of the nice things to come out of tensor networks is that the MERA tensor network is a nice way to do real space RG. So if we can think in terms of applying a MERA to a grid. Now, at small spacings, the kinetic energy is the dominant energy. So we can think about this in terms of fermionic single particle gates in 1D as sort of composing the MERA. And these are exactly the same fermionic single particle gates that we've been talking about in the conference. Okay? If we write down the simplest MERA layer, it looks like this in 1D, it looks like this two-layered circuit, sort of like you'd see in a Trotter breakup. Each layer has a single fermion gate with just one angle parameterizing it. Okay, and we can think about this just in terms of the fermionic modes, no interaction, so that it reduces down to something simple. We can think of it just in terms of what it does to the basis that we're working in. Okay, so if we were going to use this as an RG, how would we choose the gate angles? Well, you try to minimize the energy, but it's more productive to try to keep track of the states in terms of properties of what they're complete in. So in particular, as you go through a layer, then you're going to throw out or sort of tie off some of these indices. Those are the degrees of freedom that you throw away. And so what we do is we make these guys that we tie off orthogonal to the set of low order polynomials up to some order. Then the ones that go through to the next layer are the ones that we keep, and those have to have all of the low order polynomials, so those have to represent smooth functions. Okay, so it turns out that this simple recipe with exactly this MERA layer with two angles that are analytically specified, you generate Daubachy's famous wavelets to the sort of lowest non-trivial order. So those are shown over here. Eventually, to get a wavelet, you'll take a fixed point of this as you keep decimating up, and then the original layer you started with, you can think of as the continuum. Here's going through two layers of this, and you've probably seen this Daubachy's wavelets that look something like this, so these are just generating those. Okay, so there's this. What we got here is a very a simpler recipe for generating wavelets. The unitarity is sort of built in there. And you can express the standard wavelets in terms of this very easily. Now you can ask, well, does it also lead to improved wavelets now that we can think about this in a sort of nicer way? Okay, so so Glenn Evenbley was involved in the creation of MERA, and he understood how to do clever things with this. And so he came up with these ternary wavelets, which are symmetrical. And so the little gates in between here are swaps, and then you have these ternary gates. They're symmetric, so they only have one angle parameterizing them. And so this sort of layer will generate symmetric wavelets. One of the first things you learn in wavelet theory is that symmetric wavelets that are compact are not possible. But the flaw in that proof is that they're binary gates. And so here we throw away 2/3 of the functions of each layer. Okay, and so here's the functions. We generated a number of types, and here's sort of the favorite that generate these nice symmetric functions, very smooth. And the interesting thing is that Glenn has been exploring this further. This symmetry that you get here and the nice properties means that it's good for image compression. And the tests so far are showing that it's coming out as better than the JPEG standard. So it's possible that in 5 years the internet will use these instead of JPEG, for some 5 or 10% improvement, which could be a big deal. Just a possibility. Okay, so gausslets are a variation on our ternary wavelets, but they have analytic integrals. The integrals with wavelets can be sort of annoying. You can do them, but they require many tricks. So what the idea here is to sort of recompose, not to use the fixed point, but to get the properties that you want out of the wavelet transform, but to base them on a uniform array of Gaussians. Okay? And so I don't want to go into the technical details of this orthogonalizer, but what you end up with is an analytic expression for these functions. That's the final result is the black line here, as a sum of a subgrid of Gaussians with spacing 1/3, which are the dashed lines here. And if you know these coefficients, you define this Gausslet. But this has lots of properties that the Gaussians underneath don't really have. They're perfectly orthogonal. They have completeness to 10th order. And another property that turns out to be very important is that they integrate like a delta function to a very high order. And what that means is that if you, say, multiply this by, say, x squared, the oscillations that give orthogonality to the function next to it at 1, those same oscillations also cause the integral of x squared to be exactly 0. And the integral of x fourth is exactly 0, etc. Okay, so that delta function property turns out to be important. Okay, so how is this delta function property important? Okay, so let's assume that we have one of these functions. It's orthonormal. It has the delta function property. Then you can write down the single particle Schrodinger equation and say, well, I'm going to act with the Hamiltonian, just multiplying by a potential function times your wave function, which is represented in terms of these basis functions. And what you can use use the delta function property to just sample these. And what you immediately see is that you can take the standard Uij that we have for an interaction with 2 indices and just make it diagonal. Okay? And it turns out that this non-standard approximation converges very rapidly to the continuum result as the spacing goes to 0. So over here on the right, we have this is showing the convergence of a simple 1D test case, and the most accurate is the original standard form of an interaction. But these other types, there's some slight variations on this, but these other ones compete very nicely, and they all converge to the same thing. Okay. Now, the single particle Hamiltonian is not so important, but the 2 particle are not so important to get diagonal, but the 2 particle terms are the key limitation, and this applies just as well to those. Okay, so the key point is that with a Gausslet basis, we get this Vij interaction just like it was a grid. And this is a similar property that you get from sinc functions, which are plane wave duals, which sort of, in that case, stems from the sampling theorem. But sincs are, one sort of extreme example of a wavelet. And so this is something that you can get with wavelets. You can also get it with some other types of wavelets. We think our version of the wavelets are the best, but anyway, it's not unique. Okay. Well, you can see those functions are nice and local. To change their resolution, we can do a coordinate mapping, which puts more of them near the nucleus. So we can do a coordinate mapping, just change the coordinates as long as we put in a Jacobian or a square root of Jacobian to keep the orthogonality. And that will automatically keep the delta function property. Okay, so these mappings, as long as they're smooth, they won't hurt the completeness too much. And so we can make an ansatz for a reasonable coordinate mapping. And here's what it looks like. Here's so the spacing in the variable u is uniform, but when we transform it to x, it gives you a non-uniform spacing. And so the 1D distorted gausslets that we use look like this. Okay, so how about 3D? Okay, so to make a 3D gauslet, we just take a product of the 1D functions. This 1D form is nice for doing integrals. You know, integrals are a big classical calculation. They may be a problem in some cases. So it's nice to have them just as this product form. Okay, these live on a 3D distorted grid with the typical spacings of about a half atomic unit near the nuclei and say around 4 at the outer limits for something like helium. Now, a key advantage of working with something that's written as a basis instead of just trying to do this as a grid is that we can throw in extra functions. In particular, we can throw in Gaussians from a standard Gaussian basis and just pick say the S functions, for instance, to better represent the nucleus, because the nucleus itself is a singular function. So we can throw in extra functions and orthogonalize them. Okay, so with the distortions, you can have a couple of different ways of doing this mapping to 3D. Here's the simplest type where we just have the coordinate transformation be independent for x and y. The multi-slicing is where you have sort of a tree of different coordinate transformations going over the different directions. So for x, you would have one coordinate transformation, but then for each grid point along x, you would allow a totally different coordinate transformation. And so you can get improved spacing of the functions. But they end up a little bit disorganized. We've sort of gone back to this one with a post-decimation that I'll mention. So when you add in Gaussians to this, it looks like this. So we have, the gausslets are the functions that we added a Gaussian contraction to look like this Slater-type cusp orbital. And then we orthogonalize it, and we get this wavy function. Okay, now I also show a dashed line, and the key thing that we worked on quite a while is how do we get the 2 electron integrals for what we call the residual Gaussians, the thing that's left after we orthogonalize. Because these are complicated functions that we don't ever want to have to work with the VIJKLs. Okay? So we make an approximation that we match the width of this function with a Gaussian and then use that to do the 2 electron integrals. And that's a crude approximation, but the occupancy of these extra Gaussian pieces is actually very small. Most of the work is done by the gausslets, and so this doesn't make much difference at all. Okay, so first let me show you some results similar to what this is that plot I showed at the beginning with all the different methods, hydrogen chain with 10 atoms. And it's showing, and this is before, this is from this paper in 2019, before we started putting in the Gaussians. And you can see that we're converging very nicely to what looks like the exact complete basis set, complete correlation limit in a very sort of nice, it's not, it's got some oscillations, but it's a fairly controlled way.
20 minutes, Steve.
Great, thanks. Okay, here's a sort of blow up comparing against a reference quantum Monte Carlo calculation, which we believe is very accurate, showing how accurate these results are. Okay. So let me say a little bit more about putting in the Gaussians to get this hybrid Gausslet-Gaussian basis. So here is H2 plus. And this is showing, first of all, we have all the different pure Gaussian basis sets as the dashed lines. Okay, and then we can add in not the full Gaussian basis set, but just say the S functions or the S and P functions specified by some maximum angular momentum. Okay, and so eventually, as we add our functions, this controls the spacing. We get below the accuracy, better than the accuracy of the Gaussians that started with. There's some sort of happy medium where you don't rely too much on the Gaussians. You let the Gausslets do most of the work, but you still get a big correction from having this high order Gausslet doing the nuclear cusp. Okay. So here's an example of Hartree-Fock at the 10 atom chain. And you can see that using the Gaussians instead of the original Gausslets does a lot better. That's the solid line here. We're converging with Hartree-Fock for this system to an accuracy of about 10 to the minus 5 Hartree. Okay. Now there's another, so here's results for doing full CI just on the helium atom. Okay, and so what you see here is that we're converging sort of well below chemical accuracy. But the annoying, and this is sort of testing out the different parameters of the distortion. But the key thing is that there's sort of a slower convergence in this regime. And so this turns out to be because of the electron-electron cusp. Of course, that's singular, so it means everything converges slowly in this. And this is, of course, well known. Okay, but because our functions are so local, we can think of corrections to take care of this, sort of extrapolations that are easier than in a conventional basis. Okay, so if you think about where does this cusp problem come in, it's really when two electrons happen to be on the same Gausslet. If they're on different Gausslets, the basis is just doing fine. Okay, so the energy of this system for that part of it, when they're both two electrons are on the same Gausslet, looks like this, where this di is the double occupancy. Okay, and in a complete Gausslet basis, this double occupancy, and the density per Gausslet goes to 0. It's just per function. So what about a correction that looks like a delta VII? So we explored with this a little bit. You can think of you can be inspired by the local density approximation and try to make it some sort of local function of some parameters. But looking at this, we found that two of these should just be dropped, the VII and the NI. And you can think about a correction that just actually depends on the double occupancy itself, which can then be combined with this double occupancy factor to get a very simple ansatz for a cusp correction that just has these two empirical parameters. The empirical means they're fitted to Gausslets, but they're not fitted, hopefully they're independent of the atoms or molecules you're looking at. And so that's our ansatz for a cusp correction. Okay, so here's applying this cusp correction to the helium atom, where we optimize we optimize first just for helium, and then we try to optimize over a set of different atoms. So now we're on the micro-Hartree scale. The uncorrected thing is up here, and you can see that this correction, this form is working very well. Okay, and we made a universal choice of parameters that are good for 3 or 4 different 2-electron systems where we had very accurate data. And these were these parameters. This is helium. Here it is applied to H2 as a function of internuclear separation. And this cusp correction kills off most of the cusp very nicely. And you're sort of down at the micro-Hartree or tens of micro-Hartree level with sort of accessible Gausslets. So we're hoping that this is much more universal than 2-electron systems, but the tests for that are underway. Okay, another direction that we're working on is to try to do further decimation to try to get the number of functions really down to the level of similar to the number of Gaussians you might have. And here's a method called face decimation. So the key, it's easy to decimate a system. It's just sort of contractions over the functions and keeping some, but we want to keep this diagonal approximation, and that's quite hard. Okay, and we know how to do this mostly in 1D for sort of wavelet transforms.
We're at 25 minutes, Steve.
Great. Okay, this is the last slide except for the conclusions. So you can do finite wavelet transforms and do a further decimation that so far is working quite nicely. And so that's what we're pursuing. That should reduce the number of functions quite a bit more. Okay, so to conclude, how you set up a Hamiltonian has a big impact, and Gaussian basis sets are not necessarily optimized for quantum computers. Gausslets are local, smooth, orthogonal bases with larger n but diagonal interactions. We can use them as an intermediate basis for further reduction, and that wasn't shown, but we have a paper for applying that in the quantum computing framework. And then the local nature appears to allow good cusp corrections, which can potentially increase the accuracy by, say, an order of magnitude. And we have further work on decimating the Gausslets to bring in size parity similar to Gaussians. Okay, thank you.
Great, thank you, Steve, for telling us about your latest work. We have some time for questions. I suggest people just unmute themselves and ask the questions. Lynn, you're unmuted, but are you trying to say something?
We can't hear you.
Okay, while we're waiting for Lynn, I'll ask a question, I suppose, which is, so Steve, the Gausslets are of different size. So when you are computing this cusp correction, does that play a role? For example, if you get close to the nuclei, I assume some of the Gausslets are small. And would that affect the parameters going? I would guess there's some, I would have thought there might be some parameters that reflect the length scale of the Gausslet itself.
Right. So let's see. So part of our analysis was, we didn't do a great analysis. And if Lynn comes on with his sound, maybe he has some expertise in helping us there. But so this correction was mostly an onslots, but we did think about 2 electron ions as a function of Z. And one of the key features of the 2 electron ions is that the correlation energy is mostly independent of Z. Okay, and that's what sort of tells you right away that you can scale the whole Gausslet basis and sort of decide how that's working, and it tells you that you should throw away the V dependence. Okay, so there's a part of it that's going to work in that case just sort of automatically, just depending on the double occupancy. Okay, and so we may have a good handle on that, but this is it needs some nice numerical analysis done on it, which is a little bit beyond what I know how to do, to sort of say, how do we derive, what should a correction look like? It's an interesting thing, but I don't know how to do that. Can we?
Lynn, is your audio working?
Yes.
Oh, great. Yeah, I also put the question into the chat. It's a quick question. Thanks for the nice talk. So this phase decimation seems to be very non-local. How does it still preserve the diagonal 2 electron interaction?
Yes. So the decimation occurs in 1D, and so the thing about creating our own wavelets is, which required a lot of nonlinear optimization to get all the parameters, all the properties we wanted simultaneously. Well, we sort of learned how to do that. So what you have to do is do a nonlinear optimization where you can just sort of work on this line and require it to have the moment properties and completeness properties that you want. Okay, and at first I didn't think we could do any of that nonlinear optimization on the fly, but it turns out it's not too bad. And so that's what, so the fact that it's 1D makes it easy enough to do this so that we require the moment properties. And, you know, of course, you know, this is showing just renormalizing to 3 different functions per line segment, but it could, you can, that's sort of the minimum you can do more.
Very interesting, thanks.